Okay, so this is the third video on statistical power, and in this one we're going to talk about the two of the four components that go into power. Okay, so in the last video we talked about started talking about the four components that go into power. So we talked about beta, and so obviously beta over here, this value, impacts power because power is 1 minus beta. So power is the total of this distribution minus this little part that goes below the critical value in the null distribution. So all the pink is power. So power is obviously affected by beta. So if you increase beta, you're going to decrease power. If you decrease beta, you're going to increase power. Effect size is the second one. And so we talked about how effect size is the distance between these distributions. So if you take this distribution, I can't because I don't know how to do it in this video, but if I slid this over here, okay, that would be the equivalent of increasing the effect size. So for example, if the alternate distribution mean was not 580 but 600, then the effect size would be bigger between 500 and 600, right? And in fact it would be 1 because it's 600 minus 500 over the standard deviation, which we said before is 100. So that's the effect size of 1, okay, versus an effect size of 0.8, which is what we have here. So obviously, if we pull this alternate distribution over to the right, then by increasing the effect size, the difference between the means, beta is going to shrink, and then power is going to increase, okay? So that's B and E of our bean mnemonic. So A is alpha, and we know that we can set alpha wherever we want, okay? So the standard is to set it at 0.05, which means that if any of the sample mean, if our sample mean falls in this part of the distribution defined by alpha, so that if it's the probability of getting that sample mean is less than 5%, if the null distribution is true, then that is our alpha value, and then that means we're going to reject the null hypothesis and assume that the sample comes from the alternate hypothesis. So we can make alpha smaller, in which case we would say 0.01. So if we said alpha is 0.01, we're going to move this line over to the right. I wish I could move them literally for you, but here's the line. We'll move it to the right. That would increase beta, and that would decrease power, right? Because this line is moved over. So if this line now is here instead, right, alpha, which is here, will be smaller, and then beta will be bigger, and power, which is the part of the alternate distribution that's to the right of the critical value, will be smaller. Okay? And finally, the last piece of the bean puzzle is N, which is the sample size. Now, why is N related? N is related because N impacts the standard error, which is the standard deviation of the sampling distribution, which is the width of the sampling distribution. Okay, so if as N increases, power is also going to increase, right? So we will look at an example of that. Okay, so why does the N sample size impact the power? So the N impacts the power because it basically affects the standard deviation of the sampling distribution, which, as we remember, is defined as the standard error. So the standard deviation of the sampling distribution is the standard error. So as n increases, here's the formula for standard error, as n increases, then the standard error decreases pretty dramatically, right? So we learned that before, and so what impact does that have over here on these distributions and the calculation of power? So here we can see that here we have the original drawing, but then down here what we've done is we have reduced the, we've increased the sample size of the, we've increased the sample size, and so therefore the alternate distribution has a smaller standard error, so it is much more narrow. And so the effect of that, the means are exactly the same still, so the effect size is the same, the alpha is the same. Okay, it's supposed to be. It doesn't look like it, but it's supposed to be the same. Okay, so the critical value is the same, in the same place. The effect size is the same, and the alpha is the same, but beta has gone down dramatically because this alternate distribution has narrowed, and therefore the tail of the distribution, less of the tail of the distribution overlaps with the null hypothesis distribution. So beta is lower, and therefore power is higher. So that's how the sample size increasing results in greater power. So taking advantage of these relationships, researchers can determine the power, how big the sample size has to be in order to attain 80% power. So the standard level of power is 80%, meaning that beta is 0.2. And so that's how, in a study, designing a study, you can figure out how many people you need to include in the studies so that you can get adequate power, so that you know that if in fact you do reject the null hypothesis, that it's likely that the alternate hypothesis is true. And so that's it for power. Good luck.